527.048. Okay, so just
choose one of these. So you can just call this answer 1, 2, 3, or 4. So just choose one of them. Just this would be answer number 1. This would be number 2. This would be number 3. And of course, you just put in 1, 2, 3, or 4. Okay, let's go to the next one. Okay, next one is here. And this one here. Okay, so which of the following is true? Again, 1, 2, 3, or 4. Okay, next one. Okay, let's see. Okay, next one. Is here. Let's switch to these. Okay, that one, number 5. Again, 1, 2, 3, or 4. Oh, sorry, it's not there. Number 5. 1, 2, 3, or 4. last one. By the way, if you can't see this clearly, this is not absolute value sign. It's just a square bracket. No absolute value signs are here. Okay, anybody need more time? Okay. Okay, so I think that material was easy. What was the answer to the last one? I guess it's kind of tricky, a little trick question there. This is the answer, right? But I guess some people might have put that, but this is the general answer, but it's not really, there's no n here, so in a sense it doesn't make sense. Okay? Okay, so now next week we're going to have another assignment on Coursera, but it's not going to be in this course, so I'll give that to you a little bit later. Okay, so today we finished we talked last week about marginal cost, and we said that we can approximate the marginal cost with the derivative. So marginal cost really means the cost of producing one more item. So like you're producing 100, and then you're going to produce one more. How much does it cost to produce that one more? Right? So how much does it cost to produce one more item? Yeah, so the real definition would be the cost of the the total cost of the 101 items minus the total cost of the 100 items. That would give you the cost of the 101st item. Okay, but we said we can approximate that. Usually economists will approximate that with the derivative. Okay, it's not perfect approximation, but it's very close. And sometimes they even mix it up. They say the marginal cost is the derivative. But marginal cost is really what I said first. It's how much does it cost to produce one more. Sometimes they'll even just say, oh, it's the derivative, period. Okay, but it's not quite right. It's a little slightly off, but minimally off. Okay, so that is called the marginal cost. So we did that last time. And then, what else did we do last time? Do you remember? One more thing we did was the derivative or the log functions, right? And we started with the derivative of the ln function, which is a kind of one log function. But there's more than one log function because we can have any base for a log. Not any base, but we can have many bases. And e is one base, and that's the ln function, but we can have other bases. So we also wrote the derivative for general base, right? And what was the difference? What was the derivative for ln? That was 1 over x. And the general one, that is the derivative or log base b of x was close to that. It also had 1 over x in it. We just had one more factor in the denominator. And that was ln of the b. And we saw that. So this is supposed to be more general than this, which means this should work for any b. So it should work for this one, because this is a b. Right? What's the b here? E. Right? ln of x means log base e of x. So that's base b. This is supposed to work for any base, so it should work for base e as well. But we have a formula for e, so this should what should I say? I forget the right word, but anyway, this should resolve into this when b is equal to e. So what is this? ln of e. ln of e is 1. Remember we talked about that. ln of e is 1. So this just becomes this. Okay, so we did that last time. And then we did like more complicated problems where we needed the chain rule. So we said, for example, what's ln of x cubed plus x squared? And there you have to use the chain rule. And there you have to say, and whenever you use the chain rule, you have to be able to talk about the outside function and the inside function. So here, the outside function is the ln, and the inside function is here. Okay, so we can do the derivative of that. Okay, so we did that last time. So what's up? What do we have to do now? Well, let's go to Engage. And what homework do we have to do? So we did a lot of it. We've talked about higher order derivatives already. What does that mean, higher order derivatives? That's easy. That just means like the second derivative, the third derivative, and so on. So like if you have x to the fourth, and I say, what's the derivative of that? Everyone says 4x to the third. And then what's the derivative of this? That's called the second derivative. So the derivative of that is what? 12x squared, and you can keep going. Right? So those are called higher order derivatives. Okay, so we did that. And what about this min max 2 and 3? Let's see what those are. Okay, min max 2. Okay, so how about this? Find the exact location of all the relative and absolute extrema for this function. So what's the strategy here? So we have this function, like that. And this obviously has some kind of graph, right? There's some kind of graph, right? And we're wondering what the graph looks like. And we're only wondering what it looks like between -2 and 0. And we want to know, like, where's the highest point between -2 and 0? Where's the lowest point? And are there any local minimum, local maximum, and those kinds of questions. So how do we attack this problem? One way is to do this. Let's see what that says. But before we do that, how do we attack it? So how do we, so we want to find, so we have some important words for this problem, and the words are critical points, singular points, what were the other ones? stationary, how do you spell that? Stationary, is that with an E or an R? An A or an E?
A.
What? A. Okay, thank you. Stationary points. And we had endpoints. And I think that's all. Critical, singular, stationary. Well, we also had local or relative, also called relative extrema. Okay, so if we use all these words, we can, this is how we're going to do it. And actually we go this way. This is more general. So local, relative, and extrema, local or relative extrema, we know what that means, right? That means places where like that, or like that, but also like that, sorry. Like that. Okay, those are called local or relative extrema. And the endpoints, that's clear, right? The endpoints on the interval. So in this problem, we're talking about between -2 and 0. So those are going to be the endpoints, -2 and 0. Right? So we're asking about the graph between -2 and 0. So those are going to be endpoints. And stationary points means what? So stationary points are the places where the derivative is, where the slope is 0, where this line is flat, the tangent line is flat, which means where the slope is 0, which means where the derivative is 0. That's stationary points. Singular points, so these are stationary and this is singular. Okay, this is called singular, means that, because the derivative is not flat there. Because, the derivative means the tangent line slope. But there is no single tangent line. We could say the tangent line looks like that. We could say it looks like that. We could say it looks like that, right? There's no single tangent line. So we can't talk about the slope there. What that means, when we try and calculate the derivative here, if you remember the derivative, the original definition looked like this. And there was a limit here. So sometimes limits don't exist, right? Remember way back when we were studying limits? Sometimes they don't exist. So it might be possible that this is a limit problem. So it might be possible that the limit doesn't exist. And that's what's going to happen in this case. Because there's no tangent line there, so actually when you try and do the limit, it won't work. Okay, so we could give an example of that, but I'll just state it for the time being. Okay, so the limit, so that there's no tangent line here, that's a singular point. So it's when you have a cusp, that's a singular point. So we have stationary points like this, we have singular points like that, and these two together, I think it's only these two, are called, critical points. Okay? So the strategy is to find the critical points and to find the endpoints. Let me say it more clearly. Find the critical points and find the heights at those points. So we might find, there's a critical point here and a critical point here. So what we want to do is say, okay, how high is the function here and here? So maybe it's like that and like that. Okay, so find out how high it is at the critical points, and then you also have to check the endpoints. And then from those points, you can decide where is it highest and where is it lowest. Okay, so that's the strategy. So the strategy is find the critical points, find out what the height is at those points, find the heights at the endpoints, and then just figure out which one is highest and which one is lowest, and then you can answer the question. So we have to do that for this function that they gave us, actually called h, 2 times x plus 1 2/5, right? Now 2/5, what's another way to write 2/5 and the exponent 2/5? So if I write a to the 2/5, that's equal to a squared fifth root, right? A squared fifth root. So this is the same, right? This is x plus 1 squared to the fifth root of that, right? So the fact that it's a root can cause problems. What kind of problems can a root cause? Well, actually this won't have that problem. Well, square roots can have problems, right? Where does a square root? It doesn't have a problem. You're never dividing by 0. That's not the kind of problem you have. Sometimes basically two kinds of problems. One is when you're dividing by 0. So when x equals 1, you're dividing by 0. That's one kind of problem. And then square roots are the other. Basically, we don't encounter any problems except for these two. So a square root, what kind of problem can that have? If it's negative, right? So we have to be wary of that. But actually, this isn't going to have that problem, right? Because